Hello, we're going to move forward and do this presentation as a practice for next week's Mobius Connect presentation. So I'm going to pretend that this bit here is the introduction so that I can get down into the time limit that I have. So a little bit about me. There's my bio. Instead of having them read out a lengthy bio, I'm happy to have done a lot of things in my career, but we'll let you read that when you get a chance. And now for something completely different. The electric motor system consists of incoming power and basically this is the supply to a control, whether that's a cross-the-line starter, VFD, soft start, whatever it is, to an electric motor through a coupling to the load and the driven equipment or process. Through this, there can be different things. Like if there's a VFD, that's going to be a wall for anything we're doing. But whether there's a VFD or a straight power supply, we're going to worry about things like power quality and so on. In the electric motor, you have your electrical and mechanical components, including insulation systems. Couplings can be a variety of different combinations. The load can be fan, pump, compressor. It doesn't matter. Process is whatever that load is driving. What's interesting about ESA is you can see all of this with simple voltage and or current measurements, and you get to see it all at the same time. So the technology was developed, electrical signature analysis was developed by Howard Haynes and his team at Oak Ridge National Labs in the 1980s. There was already something called motor current signature analysis. That application discovery is primarily attributed to a gentleman by the name of Bill Thompson out of the UK, who focused really on rotor testing. And for a long time, that seems to have been the direction that it was pushed, primarily because some of the companies involved were looking at just rotor testing in the utility industry. So EPRI had it and some other stuff. So there was a lot of publication related to rotors. But I'll tell you now, based upon the cost of the instrument, of the instruments in the field, if you're using it for rotor testing, you're wasting your money, basically, because I could tell you about a rotor test, a rotor bar condition, basically with a inexpensive analog clamp-on ammeter. In reality, the way Howard Haynes had seen it was you have voltage, you have current, you have power quality, you have the ability to see electrical and mechanical components. In particular, the discovery for ESA was not what has been claimed in the past in some marketing articles. It was really to look at the bearings and gears and related wear in both of those in motor-operated valves for the nuclear power industry. The team at Oak Ridge National Labs also saw it as the ability to be able to take a look at a whole bunch of equipment from a motor control center. This particular image is from a paper from Howard Haynes from 1989. And he saw it as a way to not have to climb all over the machines and go to all different locations, but actually just go straight to a motor control center. So let's get into the purpose, and that is to understand what we're doing with the electric machines. So this is just a cutaway of an electric machine I took some years back from a repair shop that I worked at. And it just shows you the rotor, and there's rotor bars, and there's basically an aluminum end ring on either side of the rotor that shorts those all together. There's a stator with laminations, and those hold the coils in place, and then there's an entire frame and cage. Matter of fact, what's kind of interesting about that, because we've heard some new technologies out there, is that's actually a Faraday cage. The magnetic fields are trapped within that machine. Now you can get some leakage to the surface, and that's usually what people think that when they think they're detecting stray flux, they're actually detecting stray currents on the surface of the machine, which is ground noise, leakage from the machine, and other conditions. But in electrical signature analysis, we go quite direct. The space between the rotor and the stator is called the air gap. That's where the magnetic field goes, and that is the transducer, just like an accelerometer that you would place on the outside of the machine, except this is a very direct measurement. As a matter of fact, not only is it direct, it's relational to the load. So if I have equipment running, every time I have a variation in the driven equipment or power supply or whatever else, it always passes through that field and it has an impact on that field, and I measure that back as a relationship primarily in current. But voltage is if it's nice sinusoidal, perfect, no issues, nothing sitting there, no harmonics, then anything riding in my current is very, very definitely going to be whatever defect I'm looking for. If I have a good air gap, meaning that the rotor is dead center inside the machine, and I have that clean waveform come in, I will have a clean waveform go out. If the rotor's off to one side, in vibration this is often referred to as an unbalanced magnetic pull. The rotor's pulling to one side inside the stator. That will come out to be a calculation based upon the number of rotor bars and RPM. And if it's orbiting inside the air gap, whether that's a mechanical orbit or a magnetic orbit. A magnetic orbit means the rotor's sitting dead center, but there's an unbalance in the fields in the rotor that cause it to appear to orbit. That's called dynamic eccentricity. You can have one, the other, or both. The other things you can have is an unbalance. You can have torsional issues. As a matter of fact, that's how we read load, is not only does the side-to-side movement of the rotor inside the air gap causes permutations that we'll be looking at, but the torsional issues come out exactly the same types of frequencies. So if I have a bearing out on the driven equipment, as the motor has to drive through that defect, it's seen as a small permutation in that air gap. Unbalance, misalignment, belt tension, and of course, any smearing or lamination damage on the rotor can cause it to bow, which would, by the way, cause a dynamic eccentricity. So now let's start talking about machines in application. Now you notice in this one there's some funky things going on with the feet. And you'll also notice the location of vibration transducers. This is often a problem in application. When you get back off the end shields of those motors, of the motors, the high frequency noise, or the high frequencies we need to see to identify early bearing wear, well, those disappear because we have a transition point, so we no longer see those. So now we have basically these things mounted on a bell. So you're away from any solid structure inside the electric machine, plus they're mounted basically on the paint. You can see the paint isn't even scraped away. They're just tabbed on there, glued on the side, glued on the top. What am I going to see from that? Well, I will see things, but they're going to be very gross, meaning they're going to be very, very far along in the fault stage. So we're going to talk about how ESA gets around this. You'll also notice in here the shims are behind the bolts, away from the center of the motor. So that will be a final case study. A few things to consider while we go through this. As you hear me use certain terms. Running speed, you're going to see me using hertz in this, because for me, because I do vibration and I do ESA, I try to do my vibration in CPM and I do my ESA and current signature in hertz. So hertz is RPM divided by 60. Synchronous speed, which you'll hear, that is the actual rotating speed of the magnetic field in the stator. That is 120, which is a constant, times the applied frequency divided by the number of poles. It's always, in this particular one, it's in groups of 2, so 2, 4, 6, 8, 10. So if I have a 60 hertz machine, that's 7,200 divided by 2, which is 3,600, 1,800, 1,200, etc., etc., etc. Slip is what we actually get because the motor can never keep up with that turning field. It always has to fall behind a little bit so that the magnetic fields cut across the surfaces and cut across the rotor bars in order to develop torque. And that actually varies based upon the load. So the heavier the load, the more slip occurs. So the nameplate running speed is when we're at full load. The NS is the synchronous speed. That is basically the speed at synchronous. So synchronous speed minus the actual running speed divided by synchronous speed times 60 gives me this slip frequency. Pole pass frequency is twice the slip, or some people do poles times the slip. So twice the slip frequency or poles times the slip. Both are the same number. Now, if I'm looking at my decibels, which we do decibels versus inches per second or millimeters per second or whatever, it's 20 log 10 of the current of interest divided by the primary current, meaning the current at line frequency. Why is this important? Well, as my load varies, my current varies. So that means that if my primary current is varying, my defect current is also going to vary, and it ends up being that I will only have a change of 1 to 3 dB depending on the type of fault based on load. So I can look at a no-load machine, see a defect, and it's going to be about the same as if I fully load the machine in most instances. There's special cases, and that's part of what we would do for troubleshooting where that's not the case. So some of the motor faults we're going to look for. Stator mechanical, the running speed times stator slots with the line frequency sidebands is what we're going to see. It's an amplitude modulated signal, so we're not going to see the primary calculation like we would expect to see in vibration. We're just going to see sidebands. So static eccentricity, same thing. That's going to be running speed times rotor bars. Line frequency, 3 times line frequency, sometimes 5 times line frequency sidebands. So 120 hertz in a 60 hertz environment between each one. Dynamic eccentricity has running speed around those static eccentricity sidebands. If I see both static eccentricity and dynamic eccentricity, it's called mixed eccentricity. When I do see pole pass frequency peaks, I can actually use a chart. This chart was developed by Oak Ridge National Labs specifically for a project they did after 1989, and then they also coordinate a little bit with NASA. I'm sorry, not NASA, NAVC. The next part is how do we get our data from current to our spectra. So if I'll take a look, that's a current waveform. In that case, it's 120 seconds. I jump down to the right. That's the waveform, and you can see how it's a little thick and everything. Those are all the permutations, all the ripples sitting in the current. Those are what we're going to be analyzing. But the bigger sine wave, that's my line frequency, so that is everything's going to be related to that. So when we do start doing data, just like vibration again, we have to worry about resolution, Nyquist, and the FFT lines. So if I take a look and I have a sample rate, basically the resolution is 1 over the number of seconds, or basically the bin size. The Nyquist for ESA and current signature analysis is 2. Unlike vibration, where sometimes it'll be anywhere from 2.1 to 2.5, I use 2 because anything that I would see come back from higher frequencies, that is going to be way over 10 kilohertz. FFT lines, or the FMAT, or the number of lines basically for 22,050 hertz in this particular instance. It's a system that does a 44.1 kilohertz data sampling, tested for 110 seconds. That gives me 22,050 divided by 0.009. That's 2,450,000 lines. Now, why is resolution important? Well, because there's a lot going on because you're seeing everything at once. It's not like vibration where, I can have a resolution or a bin size of 60 CPM or 1 hertz. I have to get down into fractions of a hertz. So that 0.008 or even 0.01 becomes really important if I want to look at low loads as well as heavier loads, and we'll talk about that in a second. So in this case, if you take a look at the top, this is spectral analysis on just 30 seconds of resolution. I'm sorry, just 30 seconds of data collection. And you can see that, there's definitely peaks there and everything. We're zoomed in pretty close, so it looks pretty good. As a matter of fact, a lot of people would use this because the data set would be very small. Spectral analysis 60 seconds, you can see that some of those peaks are starting to sharpen up, and there's other peaks showing up in there. And if you go down to 110 seconds, you can see that some of those peaks are actually combinations of peaks, so they appear higher or they appear wider up top, and now they're sharper, so you can actually see other distinctions, like those peaks in close to the primary peak. Those could be conditions related to slow speed components on the output of the machine. The other peaks, those are actually pole pass frequency. And then again, on the right, same type of thing. This becomes important when we start looking for machines sitting on, say, the shop floor. Here's a good example of that. So if I'm looking at an unloaded machine, and this is an unloaded machine running at 50 hertz, on the left at 110 seconds, you can see that the bin size is good enough that I can look at pole pass frequency peaks at 0 load. That means that I am looking at the condition of the rotor at 0 load, uncoupled with full voltage on a power supply. On the right-hand side, this is where I just take a 30-second snapshot. It's now blended in with my primary peak, meaning that I cannot distinguish those pole pass frequencies, so I'm not aware that there's casting voids present in that rotor. This becomes more serious if I actually have broken rotor bars in those conditions. This is a larger spectra. I know it looks a little noisy. The vertical blue lines, those are actually line frequency. So what you often do when you take a look at something like this is you will want to see what are basically harmonic peaks and what are fault peaks. So you will notice that there's a primary peak. The peak is at 0 on the far left. That's because we're going to count from the top down 2 peaks. So when you see dB down or minus dB, that's because we're counting from 0 down towards whatever the peak is. So the highest noise, if you want to think in this in terms of sound, the highest pressure or highest noise, highest force is going to be at line frequency. All the way out there to the right, you see around 4 kilohertz. That is because this is on a VFD. That's the firing frequency of the inverter. This is going to become very important in something else we cover in a little bit. Now, if I zoom in at that 0.009 hertz, you can see I'm picking some stuff up here. There's a few things going on. Not clear on what those are yet. We're going to get into that. But basically, if I zoom in, I can see a lot going on. Plus that raised noise floor right there, which is actually, normally if I was looking at a pump or a fan, I would refer to that probably as, cavitation or turbulence. This is actually turbulence from the fan on the back of the motor because it's got an induced defect. Now, what you need for everything is the nameplate information. So this is basically, this is going to be for a case study, but 45 horsepower, it's actually 60 horsepower, it's 45 kilowatt. The 45 kilowatt selected because we're going to do an energy analysis when we do that, number of rotor bars, stator slots, and bearings. When you do the analysis in order to evaluate it, this one's running at 60 hertz. This is that machine. You can see the current up top. There's some other things we can add in. We'll end up adding into our software later, but basically RMS current and peak current becomes very important for a specific reason. But motor speed over there on the left, This is auto-detected with most of the ESA and current signature analysis devices. It's actually extremely easy to do. We've heard people talk about that you can't detect running speed, but in fact, you can detect it more accurately than you can, down to 0.01 RPM often. So that becomes important because that allows us to identify conditions, including individual components of, say, a bearing. So if we take a look across this, and you see over here on the far right, now this is current signature analysis, so we're going to take some assumptions. Knowing what those are, knowing what the voltage is for the machine, and knowing that the bands are for what's allowed to be on the machine for voltage, we can make some assumptions so that we can use watts and energy in order to do some calculations to see how severe conditions are. So on this particular machine, we can see, as we look down at the pole pass frequency, so it says check rotor bars, and we're at -40, which is actually pretty severe. It's only 14 watts of loss. Well, smaller machine. And as we go down, we can see the total watts, and you can see over there where on the bearings, like 10 watts on DEOR, 10 watts on ODEOR. That means those bearings are basically the same size, right? Nope. So we actually have two different faults going on, and they're about the same value. And then we can also see the cage. So that means that, so we have the same problem going on with both those machines. And you'll notice that they're in watts. Well, that's because when I take a look at the condition of a machine, the bearings inside the motor, total losses have to come up within the efficiency of the machine. So if it's a 94% machine, 94% efficient, and it's 100 horsepower, that means I have 6 horsepower worth, or about 4 kilowatts of total losses. And friction and windage is not the highest loss in a machine by a long shot. Most of the time when we're looking at bearings, we're looking at small motors, meaning if I'm looking at 100 horsepower or less, I'm often looking at watts. I'm not looking at kilowatts. If I'm looking at kilowatts, not only can you hear that bearing, it's screaming, it's burning. You can see it easily with infrared. The other thing we need to know about is high-frequency harmonics, and we're going to talk about this during this presentation. That's the little surprise we've got added in store, and that's going to be related to why sometimes we see bearings flute even with shaft brushes in place. So here's a bearing detection on a machine, the 60 hertz machine. It's operating, if you look on the right, we can see very, very low watt rating. So that one there, if you can see, it's on cage primarily. So we say, okay, that's the motor bearing. Maybe some lubrication. But they heard a bearing noise. Turns out to be on the pump. So the bearing defect in this case has to do with the lubrication, but the other reading that we took, and this was done under the coupling and driven portion, which we looked at the conditions of the pump itself, is we did identify a dry bearing that ended up locking up on them. It's not in the calculation here, but it is most definitely one of the things that was picked up. 200 horsepower machine. This is looking at electrical signature analysis. You can see we have all of our nameplate information there. In this case, we're looking at a winding failure. Now you can see that what'll happen sometimes is we'll get some drift. So this one has about a 0.1 hertz resolution. So if it's off just by a little bit, so in reality the peak should be slightly over to the right. On these, it's primarily in current. And then you'll see side bands of that, and that's related to running speed. That turns out to be the actual winding degradation. It's not reflected in voltage, it's only in current. So that means that the winding is in the process of breaking. And we can see the losses associated with that by converting it over to a kilowatt spectrum. And in this case, you can see it's about a kilowatt with all of these peaks that are associated. With those peaks and some other stuff going on, and all the peaks added together comes out to be about a kilowatt. And the direct result of that, 1 kilowatt times 6,000 hours, say, that comes out to be about 4 tons of CO2. And we'll talk about how to calculate that in a bit. So let's go on to another case study. We're going to hit you with a lot of these. This is an elevator motor in New York City. Those are not bubbles. That's actually brass on there. Well, we know the output speed, but we don't necessarily know exactly the gears. This happens to be a really old machine, so we counted the drawing because they used to be kind of accurate back in the day. So we know that there was about 108 bull gear teeth. So by looking at the output ratio, we knew that that came into contact with about 2.5 worm gear. That means the output would be the input RPM, which is attached to that worm gear, times 2.5 divided by 108, and that would give me my frequency for related to the output of the machine. Gear mesh would be the number of gear teeth times the shaft speed. Running speed, in this case you can see that it's listed as 1200 RPM. I do have both the bearings of the same size. When we tested this, it's also on an inverter. We did identify that it was running at 17.56 hertz, so 1200 RPM, which would be 20 hertz. So it is running, of course, as you can see, at 53 hertz, so not quite 20 hertz, or just under 20 hertz. And I add that in, so it's a 0.406 output speed, or equivalent to 24.4 RPM. Now I have the bearings, so I can calculate a few things, and the software picked up that it had bad outer race on at least one bearing, so those are the frequencies we're going to look for. Now, one of the fun things is when you get involved in an operation like this, you'll have a start and a stop. 17-story building took basically 28 seconds to get from the top to the bottom. That's an unlock part and a relock part. So where it's right at the beginning, those bumps, that's holding it in place, and then it starts to travel. So we want to look from 6 seconds to 30 seconds. It's going to reduce my resolution because just like before, 1 over that's going to give me my resolution. But that should be good enough for what we're looking for because it is under load. There's my line frequency there, but you see that slope on the left. That has to do with the change in frequency coming up and going down. Once I just look in the steady area, you can see all of the peaks show up. So they have pole pass frequency sidebands, cast aluminum, meaning casting voids. You don't really condemn a machine for that. Plus then we also have some cage peaks. We have something related to the worm gear, and then we have an outer race peak. The very bottom is something called demod, where we take the line frequency out. That's great, but I can't really use that for troubleshooting other than to identify peaks exist. The reason for that is because I have nothing to compare it to, because I have to go from the top down, not the bottom up. Winding stress, which also existed in this one, is a special calculation. It does, as it turns out, and we published a paper on this in 2021 for IEEE, that it's not really it's not really a winding short, which was the original purpose of the calculation. It actually turns out to be things like improperly set VFDs, partial discharge going on inside the machine, and other conditions that are occurring that cause sparks and discharges in the winding, little lightning storms that'll be picked up in the field. Let's get to something a little more recent. In this case, we've got an electrical signature analyzer there on the left that is taking one phase of current because it was the safest thing to get to with the time and access we had. We actually had to leave the room when things ran, so we had it set up to trigger. That's the machine there on the right, and those are wind turbine generators. They were having problems with their dyno, so we went ahead and tested it. And you can see that oscillating current on top. So we knew right away we had some kind of rotor bar issue in the machine. And you can see the pole pass frequency peaks there, and we're about -40. It is a copper rotor bar machine, so that actually means I have fractured bars. So we'll go ahead and put it at a higher load. We also see that there's a potential bearing issue. And by the way, also some gearbox issues. We went ahead and duplicated this in current signature only. You can also see that 2 kilohertz and 4 kilohertz, so the firing frequency is set for 2 kilohertz. Now, they did also detect bearings in the machine. Okay, you can see that in both cases. And then this is at the higher speed and under load. But we also looked, and the reason we did current signature is because this particular system is designed to look at supra-harmonics. That's harmonics greater than 2 kilohertz and under 150 kilohertz. And out here you can see where those frequencies are very high. Well, what happens, well, we'll talk about that in a second, because they did have shaft brush on here, but it was basically bypassed because of the high frequency noise, because they didn't filter the output. So if you look at here on the top one, this is the power side, and the one below it, that's on ground. So on ground, we're at about -70, and where we hit -40 is about 7 kilohertz. So remember that one. On top, the power going in, we're at 60 kilohertz down, or about -55 at about 20 kilohertz. So if I come over here and you see this chart here, you can see that we are right in between, so we're almost at 0, and that puts us in the yellow. That means that that needs to be filtered. And the other one at about 7 kilohertz, so we come up here in between 2 and 10, and we're at about -40. Again, same type of thing. That means that there's a lot of energy sitting on ground that shouldn't be there. So what does that mean? When we get into the red zones and everything else, we need to start thinking about filters. That includes, at that range, we can probably get away with a shaft brush for that, but not really for the higher frequency noise. The reason for that, and yes, complicated formulas, but let's talk about the bearing. Bearing, because of the lubrication, is a capacitor. So as I increase that frequency, its resistance drops. Now with the brush, the shunt and the material itself, that's an inductor, and then the material is a capacitance. So as I increase frequency, that is actually going to, the shunt in particular, is going to go up in resistance. And then normally when I hit about 10 kilohertz, give or take, I start seeing that shoot right up. While the bearing is shooting down, they cross each other. And if I go to the current on the bearing, the total current times the impedance of the brush divided by the impedance of the bearings plus the impedance of the brush, it's a known formula, basically gives me the total current across the bearing. And if I look at the upper right, that gives me an idea. In this case, because of the way they had this thing grounded, they were putting almost full load current on ground. That's not unusual, unfortunately, but it did occur. So they were definitely in the severe range. And sure enough, with only after short operation, it did take a couple of years, but they were basically in the process of failing the bearings. Let's take a look at a 350 horsepower vertical. Yeah, that's me in the field. And we're taking data there. So this case with current signature analysis, taking a look, we can see that it's calling out different conditions. Again, compared to another one, this one you'll notice just the way the shape is down there. It's actually operating at a higher frequency. I think about 8 kilohertz if I remember right. And this one has a little hump there, but the noise floor is a little low. That has to do with all the noise in ground and also the noise and harmonics in the system. Fan application, synchronous fan. So this one here involves a synchronous belt. and we analyze the fan, you see that there's multiple peaks at line frequency. Well, part of the reason why has to do with the settings in the drive. So we picked that up right away. You see the winding stress, that has to do with drive setting. It's a 4 kilohertz machine. And if we come down here, we can take a look at the losses. Here we know the bearings are going bad, both the drive-in and opposite drive-in bearings, because they have the higher watts loss. Wind turbines, primary concern, blowing up the rotors. So in this case, the check rotor bars actually, you look at the below part in this. They checked the defig test for wind turbines. So it says check Y rings and slip rings. So in this case, it has this particular machine has a failing Y ring. That is the rotor connection, and you can see it also has a drive associated with it. The same tower with ESA. Those pair of peaks right by line frequency, right in close, that's actually has to do with the blade speed of the blades on the turbine. This one here, 300 horsepower machine, that is, we're going to drop that one. 600 horsepower machine, this is the one with the, where they put in the shims. They used one shim pack across 3 machines and spaced it up at least an inch. In this case, you can see that there's bearing stuff there. When we take a look, and there was also things including static eccentricity, because when they torqued down on those bolts, they caused the stator to warp a little bit. Here's the losses associated with the bearings. So when we add those together, plus the pump blade, so 1.32, that turned out to be a nick in the blade. Somebody must have dropped it when they were putting the pump together. The cage, quarter kilowatt, 250 watts. The ball bearing, 580 watts, and the outer race, 440 watts. There is that impeller blade damage, which is an additional 2.9 kilowatts. We add all that together, that's 5.5 kilowatts worth of damage to that machine. A lot of it from half of it's from, 2/3 of it is from the impeller and blade. 1.27 is from the bearings due to the problem with the feet, and that comes out between the two conditions to about $5,500 a year. And if it's operating 80,760 hours per year, the cost reduction for correcting that or the climate adjustment for correcting that would be 0.699 metric tons, which is 2,240 pounds per metric ton. So it's 0.699 metric tons of CO2 per megawatt hour. That works out to be about 33.6 tons of CO2 per year for doing that correction. So let's hit one more case study here if we got a chance. This is a GE wind turbine. What they had done is they had replaced a bearing, and they had set the coupling back up to the gearbox, and they did a before and after. And this is really good because it just so happened we had the exact same wind speeds and everything else. Everything was exact within a couple of watts, a couple of kilowatts. So 1.6 megawatt Hitachi 6-pole 6330M bearing. So there were other issues with the gearbox. That's what all those pink arrows go to. But it was noticed right after they put everything together that some peaks showed up related to bearings. So it took a look in there, and as a matter of fact, not only did very, very small peaks show up on the bearings on the machine that were just perceptible as well in vibration, but there was a sizable peak in the high-speed gearbox thrust bearing, which the vibration transducers did not see. So they said, "What do you think it is?" I said, "How about spacers on the coupling?" And it turns out they had left out a spacer. So they sent me the gear, the bearing. I had them disassemble it. They were supposed to send the cage too. They did not. So when we took it all apart and we took a look at it, the inner and outer race peaks were very small, but you can see the false spinelling on the inner and outer race. And then the ball, which was the higher peak, you can see that one of them had smeared a little bit, meaning it got caught in the cage, which is part of the reason I wanted the cage. So they replaced it and they put the new one up there, and as you can see, they were able to retest it. So they dropped from 11 kilowatts to 2.4 kilowatts of total losses for all of those bearings. And they still have a gearbox issue. So let's take a look at that foot issue. This is static eccentricity in this case. There's my peaks associated with static eccentricity, 0.85, 0.1, 0.1, so that's about 1 kilowatt. And so that would come out to, so 0.85, and the other part had to do with another alignment, but they didn't fix the feet. In any case, 1 kilowatt, again, about 4, it goes back to that other condition we were looking at. And with that, thank you very much. If you have any questions, now would be the time.